Okay, well, thank you very much. So this is a talk about something which I've been working on for 10 years or so now, called Generalized Geometry. So I ought to introduce it to you in the first few minutes. And what does Generalized Geometry entail? It entails using the intuition of a differential geometer in a slightly different way. And some of the things which come out of this seem to be related to some of the ideas that come from supersymmetric theories in physics. But you don't need to know that. You just need to think about this new situation with your differential geometric eyes. So let me just briefly say what the idea is. So the idea is that you replace the tangent bundle on a manifold, where we usually do differential geometry, by the direct sum of the tangent bundle plus the cotangent bundle. So this has on it a natural inner product. It's not positive definite. It's just the contraction of a tangent vector on a one form. And so it has this inner product of signature n, comma n. But you think of that as being the analog of a Riemannian metric. And then instead of the Lie bracket of two sections of the tangent bundle, you have this more complicated object called the Courant bracket of sections of the tangent bundle plus the cotangent bundle. So a section of the t plus t star is a vector field plus a one form, and we have this so-called Courant bracket, which as far as the vector field is concerned is just the Lie bracket, but then we have this complicated combination of vector fields and one forms on the right. And the thing to remember about this is that it's a skew-symmetric bracket, but it does not define a Lie algebra because the Jacobi identity doesn't hold, but a particular identity does hold, that the Jacobiator, the thing on the left, is not zero, but it's d of something. So it's d of some function which is produced out of these three sections. Okay, so that's the idea, that you think of t plus t star instead of t. You think of this bracket instead of the Lie bracket. And the one thing which, the most important thing is that you have this transformation by closed two forms. So if I have a two form, then it transforms t plus t star to itself in this fashion. Okay, so you just add on to the one form part the contraction of the two form with the vector field part. And it turns out that this, if you like, preserves the natural inner product. And so it's an orthogonal transformation with respect to t plus t star, and it also preserves this bracket as long as B is closed. And so this is the new feature, the essential new feature of this type of geometry. It means that you can pull things around by diffeomorphisms, but that's what we do all the time in differential geometry. But you can also pull things around by these B fields. And so most of what I'm going to be interested in this talk is examining in a particular situation this so-called B field action. So the terminology comes from physics, but you don't need to know anything about that. Now the most interesting geometric structure that you can impose in this generalized geometry is what's called a generalized complex structure. And so, as I say, we adapt our intuition about ordinary differential geometry to this new situation. And so, what do we define? And so we say that a generalized complex structure is a complex structure on the vector bundle t plus t star, which is compatible with the inner product, so it's skew-symmetric with respect to that inner product, and satisfies an integrability condition, which says that if you complexify this and you look at the, if you like, the 1-0 part of this complex structure, so you look at a section of t plus t star complexified, which is the plus I eigenspace of J, then if you take the bracket of two such things, this is the Courant bracket, then that again is in the plus I eigenspace of J. So that is the direct analog of the way in which you define, or one way in which you define an ordinary complex structure on a manifold, which is where you say you have an almost complex structure, a complex structure in the vector bundle T, which is compatible, which satisfies this integrability condition. Well, of course, in this whole area, you can follow your nose, you can produce analogues of ordinary differential geometric objects, but there's no guarantee that it's going to be an interesting area to study. But in this case, it is, because there's some standard examples. On the one hand, a complex manifold. So an ordinary complex manifold is a generalized complex manifold. In this case, there's a convention here, but I've called it here the minus I eigenspace, is spanned by 0, 1 forms and, if you like, 1, 0 vector fields. So the holomorphic vector fields and anti-holomorphic 1 forms. This is, you can check all those conditions, and this is, so an ordinary complex structure satisfies this. But at the other extreme, a symplectic manifold also satisfies this condition. So if this is the automorphism of the T plus T star, omega is the symplectic form, this is the plus I eigenspace. So we have this mixture of vector fields and 1 forms with an I in there, and that's, so that defines a generalized complex structure. So this was one of the initial appealing features of this, that it's a common framework for both complex manifolds and symplectic manifolds. But there are other examples, in particular holomorphic Poisson manifolds, but I won't be talking about those in this talk. In fact, in my plenary talk, I'll be talking about holomorphic Poisson manifolds. But I just wanted to point out here that they do form part of this generalized geometry picture. And again, so as I said before, you can pull things around with diffeomorphisms, just as you can in ordinary differential geometry, but you also have closed two forms. And this fits into the generalized complex picture very well, because it says that if you actually take any function f, and take d of it, so that's a section of T plus T star, then you apply j to it, and that gives you a section of T plus T star, so it gives you a vector field and a 1 form. And if you look at d psi, if you look at this mixture of vector fields and closed 2 forms, then these actually preserve the generalized complex structure. So, for example, if I had a symplectic manifold, and I thought of that as a generalized complex manifold, then actually this would pick up the Hamiltonian vector field of the function f. Okay, so the most important thing, actually, that I'm going to be talking about in this talk is about just thinking of an ordinary complex manifold as a generalized complex manifold, and understanding the B-field action on certain objects, which are the natural generalizations of holomorphic vector bundles. So the point to note here is that, in a complex manifold, what I said was that the 0, 1 part, so by this I mean the complexification of this, then I split it up into the plus I and minus I eigenspace of J, so the minus I eigenspace is 0, 1. Then, so if B is a 2 form, which is of type 1, 1, so it involves dz's and dz bars, then the B-field action actually preserves this. So you can just see it, that it acts on a vector field inside here as d by dzi plus the contraction, but this is a 1, 1 form, so that contraction is actually a 0, 1 form, and so we get something which still lies inside here. So the way we can think about this is that if I have a closed real 2 form, which is of type 1, 1 with respect to a complex structure, then I can think of that as a symmetry of this. It's something which preserves the generalized complex structure. And what it means is that actually even ordinary complex manifolds have Hamiltonian functions which generate symmetries. It's just that the symmetry is not a vector field now, it's a closed 1, 1 form. So I suppose I should have put an I in there. So the function f gives us a 1, 1 form dd bar f, and if you like, 1 over I times that I can think of as a B-field symmetry. So this notion of generalized geometry sort of restores the balance between complex manifolds and symplectic manifolds, particularly in the sense that a function generates a symmetry. Well, that's a very brief description of what's going on here. You can read more about it in lots of different places, and so there's a considerable Brazilian presence in this area. So my former student, Gil Cavalcanti, in fact, when was that? 4 years ago, he gave a course here in the 26th colloquium, so somewhere or another. I imagine there are the lecture notes from this course. And here are a couple of recent papers, including one by Enrique Burstein, who is here, of course. So basically, the main features of generalized complex geometry were developed by my two former students, Marco Gualtieri and Gil Cavalcanti, and there are a lot of papers by them. Okay, so now, so that's the basic setup. Let me now talk about the topic of this lecture, generalized holomorphic bundles. So the idea is, how do you generalize into this generalized geometry setting the notion of a holomorphic vector bundle? Well, the first thing you look at is the d-bar operator. So we want to define an analog of the d-bar operator on functions. Well, there's an obvious way to do that. So you take a function, you take its derivative, section of the cotangent bundle, that sits inside. So here I'm using it's a bit painful to keep on writing t plus t star, so I just want to call this E. I should say that there are what are called twisted versions of this, where E is actually an extension of the cotangent bundle by the tangent bundle, a so-called Courant algebroid. But for the moment, most of this, I just want to think of E as being, anyway, t plus t star. So what do? We take a function, we take its derivative, that's a section of the cotangent bundle, that sits inside E. E, complexified, splits in terms of a 1, 0 and a 0, 1 part, and I just take the 0, 1 component. So this again is the complete analog of defining the d-bar operator for a complex manifold, because you take the function, you take d of f, and then you split the complexified cotangent bundle into 0, 1 and 1, 0 parts. So what happens in the two typical situations? Well, for a complex manifold, the only 0, 1 part that contains derivatives, that contains forms is this. So actually here, you just get the ordinary d-bar operator. And for a symplectic manifold, you get this more complicated object here. And it's here that, if you like, the two different disciplines of symplectic geometry and complex geometry kind of part ways. They go off in different directions, because whenever you start thinking about complex manifolds, I mean, the way it's developed is that in algebraic geometry, you think of the ring of functions, or the local ring of holomorphic functions, and you look at modules over that. And that's all very well, but if you try to do that in the symplectic case, then it's easy to see that d bar f equals 0 if and only if f is locally constant. So these are, this imposes limits on the extent to which you do take some construction in ordinary complex geometry and try and adapt it to this generalized situation, and you suddenly see that actually you can't do everything. You can't talk about rings of functions. At least it's not a useful context to look at symplectic geometry. Okay, so what can you do then? But in general, you look at this. This is the way you define the d-bar operator. And then in the usual fashion, you can extend it to a d-bar operator on exterior powers of this bundle. And what is the usual way? Well, the usual way is just the way that you define the exterior derivative in terms of the Lie bracket of two vector fields, except here you use the Courant bracket of two sections of t plus t star. There's only one point about this, and that is that although you can extend it, you can make a definition of a differential operator going from, if you like, 0p forms to 0p plus 1 forms. It's not immediately obvious that d bar squared equals 0, because in the usual situation, that depends on the Jacobi identity for the Lie bracket of vector fields. And as I told you earlier, the Jacobi identity doesn't hold in this situation. On the other hand, the definition of a generalized complex structure means that, well, first of all, the compatibility of J with the inner product means that when you look at the plus I eigenspace, then that is isotropic. In other words, the inner product is completely zero on that. And so what that means is that if you look at this this formula here, then the closeness, the closure of sections of E01 under the Courant bracket means that this term here, if U and V are sections of E01, then this also is. But here we've got an inner product, and so but this inner product vanishes because this is an isotropic subbundle. So actually this right-hand side vanishes if we're looking at sections of E01 or its dual. And what this means is that actually the Jacobi identity does hold, which means that d bar squared is equal to 0. So you can define this way a whole complex, a whole elliptic complex on a generalized complex manifold. And so this is the way that we try and introduce the analog of a holomorphic vector bundle. So in ordinary holomorphic geometry, you think about this in terms of holomorphic transition functions, if you like. Well, we can't do that because, as I've said, in general, there's no local ring of holomorphic functions. And so what you do is to adapt an equivalent definition of a holomorphic bundle, which was originally due to Malgrange. And that is to say that, so this is just in ordinary holomorphic geometry, you say that a holomorphic vector bundle is a C-infinity vector bundle, V, which has a differential operator, d bar, capital D bar, going from this, whose symbol, if you like, is the ordinary d bar operator, and such that d bar squared is equal to 0. So this is Malgrange's definition. What it means is that, in particular, if you choose a connection and the connection has whose curvature has no 0-2 part, then this defines such a d bar operator. But you don't need the connection to do that. So this is a definition. So this definition at the top doesn't make sense in generalized geometry because we don't have a local ring of holomorphic functions. This definition does make sense, and so this is what you adopt. So you say that a generalized holomorphic bundle is a C-infinity vector bundle V with a differential operator, but now we replace that, the 0-1 forms, by sections of E01, such that the obvious operator, which is composed out of this in the same way as the extension of the d bar in the ordinary case, that satisfies this integrability condition, d bar squared equals 0. So it's as I say, all we do is we take an object which we understand in ordinary differential geometry and we adapt it to this new situation. And of course you can get an elliptic complex out of this, and if you want you can look at the index of this, which is a rather boring number. It's just the Euler characteristic of the manifold times the rank of the bundle, which is it's compatible with with this particular case here. So actually, if you look at the symplectic case, then a generalized holomorphic bundle is just the same as a bundle with a flat connection. And in the holomorphic Poisson case, it's what's called a Poisson module, which is a very interesting object. But in the ordinary complex manifold case, you might think, well, an ordinary complex manifold, we think of it as a generalized complex manifold. The most obvious thing is that an ordinary holomorphic bundle is the same thing as a generalized holomorphic bundle. And it's an example of that, but in fact it's something a bit more general, and because it's a bit more general, that means it's something more interesting, and it's what we call here a co-Higgs bundle. So for the rest of this talk, I'm going to be talking about these things, I'll tell you what they are, co-Higgs bundles and the action of the B field on these. So what are they? And why this strange name? So this is what it is. So remember, now we're just on an ordinary complex manifold. And I'm going to take an ordinary holomorphic vector bundle, but I'm going to take something extra on it. And so I'm going to take a holomorphic section of the bundle of endomorphisms of V tensored with the holomorphic tangent bundle. And it has to satisfy a nonlinear condition that phi squared is equal to 0. So if you like, phi wedge phi is equal to 0. So that means it's the object in here, which is the Lie bracket of phi with itself. Lie bracket, I mean bracket in terms of endomorphisms with itself, together with the wedge product of the two forms. Now, of course, so if I took phi to be equal to 0, then that would be an example, and that would just be an ordinary holomorphic vector bundle. So it is equally true that an ordinary holomorphic vector bundle is an example of a co-Higgs bundle, but the co-Higgs bundle is in principle more general. And now, what about this name? So these are what are called Higgs. So what's the difference there? Can you see any difference? Well, the difference is there that many years ago now, it's 25 years ago, I introduced on a Riemann surface a set of gauge theoretic equations which were based on the same data on a holomorphic vector bundle and a section of the endomorphism bundle tensored with the cotangent bundle. And then, more or less the same time, Carlos Simpson, coming from a very different angle, he looked at these things on more general Kähler manifolds, and it was he who called these things Higgs bundles. I mean, I called them Higgs bundles because the structure of the equations, the gauge theoretic equations, meant that this phi here was behaved like the Higgs field in certain Yang-Mills theories, and Simpson called these things Higgs bundles. So a co-Higgs bundle is basically the same thing as this, but you replace the cotangent bundle by the tangent bundle. And that has certain important consequences. And what about this integrability condition, this phi squared equals 0? Well, all that means is that if I write this locally, if I write this endomorphism of the vector bundle with values in the tangent bundle, if I write it like this, so this is using the summation convention, then this coefficient vanishes. In other words, each of these components, phi mu, actually mutually commute. So each of these components is a local matrix, if you like, and here we're just looking at the commutator of these matrices. So what is it? So that's the data, and how do you get this d-bar operator out of it? Well, again, it's easier to write it in terms of in local terms. So here, if you like, is the d-bar operator, which in Malgrange's sense defines the holomorphic structure on V. And here is the extra term. So this on the right-hand side, you see, this is lying inside E01. It's got a vector field component and a one-form component. And it's this Higgs field which appears in the vector field part. So the equation big D bar squared equals 0 implies various things. It implies, first of all, that this is an ordinary this is an integrable holomorphic structure on this vector bundle. It implies that phi is holomorphic, and then thirdly, it implies that this phi squared is equal to 0. So it's algebraic condition. So the first thing you can ask is what examples can you find of these? And you can take some trivial examples here. If you took the vector bundle to be the direct sum of a line bundle and its dual, and took phi to be a section of L squared T, so that's a section of the homomorphisms from this to this tensor T, so that would be an example. So if you want examples, you could just take L to be a line bundle of positive degree on some algebraic variety, raise it to, if it's high enough degree, this vector bundle will have holomorphic sections, and then you can find such things. Actually, every manifold has a canonical one of these, so it looks like this. So this is, of course, rank 1 more than the dimension of the manifold. So the vector bundle is 1 plus the tangent bundle, and this is the Higgs field here. Okay, so it takes lambda and x to x0. So x here is a section of this tensored with the tangent bundle. And but more interestingly, actually way down in one dimension, on the projective line, so the most simple situation you can consider, then you can find lots of them. And this involves an algebraic geometric construction called the direct image sheaf. So let me very briefly say this is a geometry seminar rather than geometry session rather than algebraic geometry. But it's an interesting situation about what happens in dimension 1. So on the projective line, the tangent bundle is the degree 2. So that's the holomorphic line bundle O2. So what about a vector bundle V? If it's an ordinary holomorphic vector bundle, then it depends on the first Chern class, but the generic situation where C1 is equal to 0 is that V is a holomorphic to trivial, and then our Higgs field is simply if you like, it's a triple of matrices. So phi 0, phi 1, and phi 2 are just constant n by n matrices. So this is the Higgs field in this case, and because we're in one dimension, this non-linearity condition is satisfied trivially. So you could say that in dimension 1, I just give you a triple of matrices, and that gives you a co-Higgs bundle, generalized holomorphic bundle. If you want to study these, then the thing to do is to look at the so-called spectral curve. So you look at the characteristic polynomial of phi. And this has, of course, phi was quadratic polynomials, so these coefficients are themselves polynomials of different degrees, or more invariantly, they are sections of certain line bundles over the projective line. And then in order to make sense of this equation, we have to interpret this eta as being the tautological section of the pullback of the line bundle O2 to itself. So this spectral curve sits rather naturally in the total space of the tangent bundle. Then the construction is that you take a holomorphic line bundle on S, you take its direct image sheaf, and then the direct image sheaf of this eta, this tautological object, is actually the Higgs field. So I don't know, I don't want to go into too many details over this. The direct image sheaf is just is an algebraic geometric construction. This is what it is. You can do it also on algebraic surfaces. And so, in fact, you can, on the projective plane, you can also get examples more or less by the same fashion by pushing down line bundles on some finite covering of the projective plane. So I don't want to go into too many details about that, because I want to really talk about this. Here's another issue. Once you start looking at these objects, then you can look at the moduli space. You can introduce a notion of stability and look at the moduli space. And in fact, this is a rather interesting object, even in one dimension over the projective line, because the moduli space has a proper map to a vector space given by the coefficients of that spectral curve, and the fiber of a generic point is the space of line bundles on the spectral curve. That's how you get these vector bundles. So the fiber is generically a torus of dimension k minus 1 squared if we're looking at k by k matrices. And I should mention that you can do all sorts of things. This is what a recent student of mine has been calculating, Poincare polynomials of these moduli spaces. I should say that that's not just what he does, but there's an interesting point about doing this, because there have been some conjectures recently by physicists, by Diaconescu and others, about iterative formulas for Poincare polynomials with a large range of moduli spaces, which are of interest both to geometers and physicists. And this is like a check. The physicist's idea is based on several conjectures, and this was a check that the conjectures actually worked out in this particular situation. So there is an interesting moduli space here, which you can look at in one dimension. But what I said initially was that the interesting feature about generalized geometry, which differentiates it from ordinary differential geometry, is that we don't just have diffeomorphisms to pull things around with, but we have B fields. And so, so let me discuss then the main point of this lecture, and that is to look at this B field action on generalized holomorphic bundles which are associated to these co-Higgs bundles. So this is just a repetition that if I have a real closed 1-1 form, then I can think of it as a symmetry of the generalized complex structure. And what that means is that anything I define in terms of the generalized holomorphic structure, generalized complex structure, can be transformed by such a thing. So in particular, it will transform, if I have one generalized holomorphic bundle, I can transform it by a B field of this type and get another one. Just as if I had a holomorphic diffeomorphism of the manifold, and I had a holomorphic vector bundle, I could pull it back by the diffeomorphism and get another holomorphic vector bundle. So the interesting issue is what does this B field transform do to one of these co-Higgs bundles? So if you look at what happens in local terms, then this is it. So you start with a co-Higgs bundle. You think of it as a generalized operator, d bar. You apply the B field, and what do? You change the holomorphic structure on your underlying bundle by adding on this. So this is a contraction of the Higgs field with this 1-1 form. So it gives me the same sort of object as this, which is it perturbs the complex structure, but it's still an integrable complex structure. I know that because this was a symmetry of everything that went along. I don't really need to check it term by term. So if I write that more invariantly, I can say that I have my B field, which is a form of type 1-1. I take the contraction or interior product with phi, which is a vector field with values in the endomorphisms, and then because phi squared equals 0, it's not hard to see that d bar phi equals 0, or I should say, in any case, that follows from the general picture. So it changes the holomorphic structure, but doesn't change a lot of things which it doesn't change. For example, it doesn't change the spectral curve. If I'm in one dimension, the actual spectral equation for the spectral curve doesn't change, but it does change the holomorphic structure. And there's another feature about this. That suppose this 1-1 form was actually cohomologically trivial. Suppose it's d bar of a 1-0 form. Then if I do the contraction of the 1-0 form, I get an endomorphism of V. And, what is d bar of that endomorphism? Well, it's actually, it's this contraction here. So if I now look at the commutator, so remember these are sections of endomorphism bundles, so it's a non-abelian theory. Things don't automatically commute, but if I look at this commutator here, then you express it, it comes out in terms of these commutators of these coefficients and the phi squared equals 0 integrability condition, so that that's equal to 0. So the net result of that is that if I actually conjugate the ordinary d bar operator by the exponential of this endomorphism psi, then I get d bar of psi. So that's something which happens in an abelian theory. This is the way that you do gauge transformations for line bundles. But the fact that phi squared equals 0 means that actually you can do this in this non-abelian situation for the co-Higgs bundles. So what it means is that actually if I take this is the trivial situation, but what it means is if I take two B fields which are cohomologous in a Dolbeau sense, then the B field action gives me two co-Higgs bundles which are equivalent under a gauge transformation. So if I look at equivalence classes of co-Higgs bundles, the moduli space of stable ones, for example, then it's just the cohomology class of this 1-1 form which acts. Well, here's some examples. So here, I gave you these standard examples earlier of co-Higgs bundles. What happens if we hit each one of these with a B field? So, in the first situation, so what happens is that instead of getting a direct sum, it gives you an extension. So the B field, when I contract that with this, so that contracts the T with a T star, I get something in the Dolbeault cohomology H1m of L squared, and that's the object which classifies holomorphic extensions, which look like this. So the trivial class is the direct sum, non-trivial classes give me non-trivial extensions. Similarly, in this canonical situation, I get, instead of 1 plus T, I get an extension. And what about this, the simplest possible case? What about this one-dimensional case? So you might say, well, it must be a pretty trivial object down here, because there's only one class, CP1, there's only one Dolbeault cohomology class there, H1 of T star, that's just the top degree cohomology, one-dimensional. Is there anything interesting really going on there? And in fact, it turns out that there is. So if you look at this spectral curve construction, then the Higgs field was obtained by taking this direct image of this object eta, this tautological section of this line bundle on the spectral curve. So if I now do this B field transform, so I take a 1-1 form on CP1, I'm changing the holomorphic structure on the vector bundle V in this way, but I can equally do that by pulling back B to the total space of the tangent bundle, contracting it with this tautological section, and saying that actually all I'm going to do is to take the vector bundle obtained by the direct image sheaf of a line bundle L, which is where I change the D bar operator on L by adding on this 0-1 form. So that is just if I think of line bundles as D bar operators on, holomorphic line bundles in terms of D bar operators, that's a linear transformation. In other words, if I multiply that by T, what I get is a linear flow on the Jacobian of this spectral curve. So, and it's a linear flow in a particularly canonical direction, because all I've done is taken the canonical generator of this, pulled it back and contracted it with this canonical object on the tangent bundle. So what does this do to the solution to the equations? Well, it actually gives you a rather interesting evolution. If I write my Higgs field as a triple of matrices which are the coefficients of a quadratic polynomial, and if I write them in this way, then you get this set of nonlinear ordinary differential equations, which appeared a long time ago when Nahm introduced them in the construction of monopoles on R3. So, rather surprisingly, this B field action actually gives you, in this simplest situation, an evolution according to these equations. These are generalizations of, for example, the equations for a spinning top. Well, finally, in the last 2 minutes, let me just go back to saying what is one context for these things apart from generalized geometry, and that is that this is an analog of the ordinary Higgs bundle equations that I began looking at together with Carlos Simpson a long time ago. And they're related to having Kähler geometry. So far, everything has been on an arbitrary complex manifold without any particular metric. But the situation with ordinary Higgs bundles was that there's a set of equations, namely these equations, that you can, on a stable Higgs bundle, I won't tell you exactly what stability means, it's a generic situation. Then there's a natural Hermitian metric which satisfies this equation here, that I take the curvature of the canonical connection on this holomorphic bundle endowed with this Hermitian metric, and this satisfies an equation of this type. So this is a Lie algebra valued 1-1 form. I take this plus this, and this lambda is if you like, the contraction with the Kähler form. It's the Lefschetz lambda operator. Then this is the equation which generalizes the Hermitian-Einstein equations if phi is equal to 0. So this is the basis for Simpson's so-called non-abelian Hodge theory, which uses the properties of this differential equation. And you can do the same thing in the co-Higgs bundle situation, but instead of this, you get this equation here. So now phi star is not a 1-1 form with values in the endomorphisms, but it's a section of the tangent bundle wedged with its with its complex conjugate, and so we contract with the form itself in order to get a scalar object here. So it's just the same picture, actually, the same type of procedure, which says if we start with a stable bundle, then we get one of these equations. So the interesting thing here is to actually to reformulate now these equations in terms of this B-field action. So now, if I take a Kähler form, now I want to consider this as defining a complex B-field. So actually, if we went all the way back to looking at symplectic geometry, then if you notice, maybe you didn't, but the formula involves thinking of the symplectic form, or I times the symplectic form, as a B-field. So with the Kähler form, what we get are two complex B-fields, but we can transform in the same way. We can transform the co-Higgs bundle by these. It's just that we now have an I in there. And so we can do it in two different ways. And that gives us two different holomorphic structures on the same bundle. Now, if you have a Hermitian metric, then, of course, again, for each of these complex structures, you get a connection. And it turns out that if you rearrange things slightly, then you can introduce, so the two curvatures of these two connections, F plus and F minus, are related to the curvature that appears in the Simpson formulation in this way. So finally, let me just show you that there's a rather interesting set of equations, if you look at it this way, which is equivalent to the Simpson version, Simpson type equation on these co-Higgs bundles, and that is this: that we have these two different complex structures. We introduce a metric. We look at the curvature of each of these, and these equations here are equivalent to this set of equations here. So you take the average, if you like, of the two right-hand sides of the Hermitian-Einstein equations, if you like, and set that equal to 0. So this is a point of view which has not been fully developed, and it raises a lot of different questions, none of which I have time to address today, about, in particular, what are the analog of the Einstein equations, even for Riemannian geometry, in this generalized complex setup. Anyway, I'll leave that with you as an example of the way in which generalized geometry fits in with some traditional equations and poses some interesting questions which I hope other people perhaps can answer. Okay, thank you.